Okay, so in the last lecture we looked at the encoder. We zoomed into the encoder, find out the different components inside the encoder. Now in this video I'm going to talk about the decoder, right? So we'll start with a very abstract representation of the decoder and then slowly zoom into it, right? So first of all, what does the decoder do, right? So here we were dealing with the task of translation, right? And in the task of translation you're given an input which is in English, and you want to generate a translation, say in any of the Indian regional languages. In this case, let's assume it's Tamil. Okay, and now the way the decoder would work is that somehow I will tell it what the encoder has seen so far, right? That means the entire input that has been already processed by the encoder, I'll somehow try to feed it to the decoder. How I'll do that, we'll see it soon, right? Once it has got this information, we'll pass the start symbol to it. So we'll say that go, start decoding the output, right? And then hopefully if things work well, then it should produce Nan here, which is the Tamil translation for I, right? Now once it has generated the first word, we want to feed that word back to the decoder, right? And we had seen this in the case of RNNs also. This is known as autoregressive decoding. Now what we are telling the decoder essentially is that after seeing everything that you have seen from the encoder and whatever you yourself have decoded so far, generate the next word, right? And the next word maybe in this case would be transformers, right? And then once it has generated that, we again feed the transformers word back to it and continue in this fashion, right? So now we are saying that, hey, whatever you have already seen from the encoder and whatever you have decoded so far, using all of that, generate the next word, and it will hopefully generate the next word, right? So that's how the decoder operates. So the main thing to note here is that it takes some inputs from the encoder, some inputs from what it has already generated, and then has an output layer for generating the outputs, right? So this is what we understand at an abstract level. How does this combine all these things, right? This is one input, this is another input, and now using all of this, how does it produce the output, right? So that's what we want to see in the case of the decoder. And with this high level understanding, now let's try to dive a bit deeper and understand what the decoder looks like. Yeah. So this is what I was explaining. It will have its own inputs. It will also have inputs from the encoder, and then it will have produce its output. What will the output be, right? What will it produce at the output? Can you tell me? Yeah. So what would say this is the first output it generates, right? So when I say output, what do I mean? What is it that it will generate at the output? It will be a vector. Okay. What is this vector? Is it just any vector or is it a special vector? No, at the output we are generating a probability distribution, right? Yeah. Right. So this is a probability distribution over what? Something which starts with a V, ends with a Y. Vocabulary. Okay. So the vocabulary of the language. Oh, you have not seen my previous videos. You find this funny. I do this regularly. Okay. So this is the vocabulary of the language, right? So every word here is represented as one of the dimensions of this v-dimensional vector, and you would hopefully want that the probability of Nan is the maximum, right? So the output is going to be a probability distribution. That means at the output layer, what is the function that I'm going to use? What is the output function? Softmax. Cool. So the output is going to be softmax. At least that much I have figured out now, right? And the input looks like some embeddings, right? I'll have the embeddings of the words. Okay, good. And what are these? I'm calling them EJs. What are these? These are the outputs of the encoder. So the encoder had a t-dimensional input as t-length sequence as input. So for each word in the sequence, it has produced an encoding, and those encodings would also be fed to the decoder. It makes sense because this is the input. You have encoded it. Now you need to pass it to the decoder. Otherwise, how does the decoder know what is the input sentence, what is the translation that I need to produce, right? So that's what the inputs and the outputs of the decoder look like. Okay. So the full decoder is a stack of n such layers, right? In this case, I am thinking of n is equal to 6. It could be 8, it could be 12, it could be 24. It could be as deep as what your application requires or what your design choice is, right? Now there are 6 layers of such decoders. Now what is happening at the input layer? You have the words generated by the transformer itself, right? And then they are somehow getting encoded, and then every word has its encoding, and at the out, so actually the first word here should have been go, right? Because once you give go, it should then generate none, which is actually the first word in the translation, and then it gets fed back, as I said, right? So this is what it looks like, the overall decoder. Is this okay? Any confusion about this? How we migrated from 1 layer to 6 layers? Is that okay? You understand what these arrows are? Output from each layer, right? And every arrow corresponds to one word in the input, right? It's the same thing that we saw in the encoder, that every word has a representation which carries on to the last layer. Is that okay, everyone? Yes. Okay. Here, except the only exception is in the last layer, you are actually generating a probability distribution, and you could choose to take the argmax from there as the predicted word, right? There are other strategies which we'll look at later, but for now, let's assume that the word with the maximum probability is the word that you're going to predict at each time step. Okay, fine. Now that we have seen like the 6 layers, right, what does the beast look like? We want to zoom into one such layer, right? What does one such decoder look like? There are 6 such layers of decoders. What does one such look like? So you have the inputs. You have something known as a masked multi-head self-attention. Okay, I think these words are familiar to you. Multi-head self-attention is familiar to you, I believe so, right? But what is masked? This is something that you have seen before in the encoder. In the encoder, we did not have a masked attention, we just had the multi-head self-attention. So a new term called masked multi-head self-attention has come, so we'll have to see what that means. Okay, so that's one new thing that we'll have to learn. Okay, then you have the inputs from the encoder, which I'm collectively calling E. So E here stands for E1 to ET, right? So there are capital T such vectors, each of some dimension T, right? And that is called the multi-head cross attention. So far we had seen self attention in the encoder. Now what is cross attention? Can you guess what does cross mean? It's attention between the encoder and the decoder, right? So that's why cross. In the encoder we had attention between the words within the encoder. In the decoder also the first block is attention between the words within the decoder, so that's self attention. And now the second block is attention between encoder and decoder, that's why we are calling it the cross attention. Then the last layer is the feed forward network, which is the same that you had in the encoder, right? So if you think of it, the encoder was actually like this, right? This was not there. This was not masked, but just multi-head self-attention. And then after this, you directly had the feed forward network, right? This is what the encoder looked like. Now here we have to learn 2 things, masked and what does cross attention mean. Right? So these are new 2 things that we have to learn for the decoder. So now, to understand why we need masking and why do we have this masked self-attention, we need to understand a concept known as teacher forcing, right? Or rather, it's one of the concepts that we need to learn in association with masked self-attention, right? So let me try to explain what teacher forcing means. Right? Now let's imagine you are training the transformer, right? You have not trained it yet, so it's still learning, right? And what's happening during training? You have the encoder, okay? You have the input sentence given to the encoder, okay? Then you have the decoder. Somehow you are feeding these encoder representations to the decoder. We don't know how, but somehow some matrix multiplication will do and feed it, right? And then you have started with go, okay? And you have generated the first word na, okay? And then this you are going to feed. And now the next word is going to depend on this as well as the encoder, right? Now, do you see any problem with this? No, we will have as many inputs as the encoder, right? As many states, right? Now, let's imagine that you are training the transformer, okay? And this is the first batch of data that you have passed it, right? The first set of sentences that you have trained. All the weights in the encoder are sort of randomly initialized. All the weights in the decoder are also currently randomly initialized. It's not a trained network. It has not learned anything, right? So what do you expect it to predict here? Will it predict the word none? It may not, right? It may predict any word from the vocabulary, right? So what will happen? Now suppose it predicts, say, I don't know many Tamil words, but I'll just switch to Hindi maybe. Suppose, okay, main is not a good example because, okay. Yeah, maybe let's say it just predicts the word Hindi, okay, the word Hindi itself. Now what will happen? So this Hindi will go here, yeah, right? And now it will say that having looked at whatever was the input, which was I enjoyed the movie Transformers or whatever it was, and the prediction go Hindi, right? Predict the next word. So what will happen now? It'll keep generating junk after this. Does that make sense? Right? Does this look like a good training strategy?
That may
No?
be beyond my
So what should we do? Remember, during training, we have the sentence I enjoyed whatever and its Tamil translation also. We have both this. Based on that we are training, right? Otherwise what's the training data, right? I have a lot of these English sentences and I have the corresponding Tamil sentences with me. So what should I do? At this point, what should I, suppose it predicted the word Hindi, what should I feed here? Can I feed the word naan? Yes, no? Do I know that that should be the correct translation? Do I know that? First let's settle. You know that. Why? Because this is given to you. Right? So you have that. So irrespective of what the transformer has predicted, you know what the correct prediction should have been. Yes, no? Then it makes sense to not rely on the transformer's output and just feed it the correct translation. Yes, no? Okay? Everyone gets that? Okay. So then I'll feed it the word none. Okay. Then why do all this drama, right? I'll just feed it the full translation here and ask it to decode. What's the problem with that? I'll have the full Tamil translation here, right? All the words. I'll just feed it, just as I was feeding the entire English sentence here, I'll feed the entire Tamil sentence here and ask it to predict. What's the drawback of that? There will be no use of encoder. Good. There will be no use of anything, right? I mean, you already have told it what the right answer is. It just has to somehow learn the identity function, right? That whatever my input is, somehow just try to maximize that. And it looks like a very easy problem to solve, right? Okay. So we have learned two sort of concepts which are competing with each other. The first concept is that I don't want to rely on the predictions made by the transformer during the initial stages of training because it's all random. So I can't take this and feed it as the next word, right? Because I know it's not going to be correct. And then I'm asking it to start with something wrong and then fix it. How will it fix it? So that's why you need to pick up the right word from the training data itself. Yes? This is what we are agreeing on, right? But the second thing that we are agreeing on is that if I take all of this and feed it, then that's useless. It's not going, it has no incentive to learn anything. It can just learn to replicate the input as it is. Why did I even need the English sentence if I'm going to give the Tamil sentence? So how do you balance between these two competing concepts? Do we agree that both are important ideas? Yes? So how do we balance between them? And now can you think of this in the context of masking? What we are trying to learn is masked self-attention. Can you think where would masking fit in here? No. Okay, can I just clean up the diagram a bit while you are thinking? Okay, this is what my encoder was. This is what my decoder was. Go. Okay, it predicted something. I don't care about what it predicted. Of course, based on what it predicted, I'll have some probability, I'll have some loss, I'll compute the loss. That loss needs to be propagated back to the network. So I need to know what it has predicted. If the maximum probability was not for the word none, then I need to back propagate to the network, right? So that loss I'll compute. That's why I care about what it has predicted. But I'm not going to use that as the next word, right? As the next input rather. The next input is actually going to be the word that is the correct translation. Yes? So if it predicted Hindi here, that means Hindi was the highest probability word and the actual translation was some lower probability. So I'll propagate that loss. I'll calculate the cross entropy loss and propagate it. Yes? Is that correct? Okay. But that's all. That's all that I care about the output for. But the next word I'm going to feed is none. And using none, what is supposed to predict? Based on the input which comes from here, right? And based on the first correct word, all of this becomes input now, right? The actual input which was I enjoyed the movie Transformers, and the actual first word, I want to predict the second word. But while predicting the second word, I don't want to see. What do I not want to see? What do I not want to see? I don't want to see what it had predicted, that's true. But I also don't want to see the next set of words. Does that make sense? Yes, no? Why the next set of words? I just don't want to see this word, right? It's okay if I see these words.
But it will capture the information that after the third word would be this, and it can, while training that transformer, it can account for that particular.
So he's saying that it will look at the words which come after this current word, right? So my argument was that if I show it that the input is transformers here, then we'll just learn to predict transformers as it is, and there is nothing to learn, right? I've just trivialized the problem. Whatever is the input, just predict it as it is. So my solution was that don't show it this word at time step 2, right? But all the other words can be shown. His counter argument is that you cannot do that because you're generating one word at a time. So when you're generating the second word, when you're going to use it for inference or at test time, you don't have the remaining words. After you give me a trained transformer, if I give you the sentence, I live in Chennai, right? And when you're trying to decode the second word, you don't have the rest of the translation with you. So you cannot see the rest of the translation. Does that make sense, everyone? Yes, no? How many of you are with me? Please raise your hands. Okay, so then I cannot feed this also. So looks like at time step 2, I should only feed words at time step 0 and time step 1. At time step 3, I should feed only words at time step 0, 1, 2, right? So if the length of the actual translation was T1 and I am at the Tth time step, then what does that mean? I should feed only T minus 1. Is that okay, everyone? That means I should mask everything which comes after T. Does that make sense? Okay. What would this look like in terms of a matrix? So let me just tell you, right? This is for first word, second word, third word, fourth word up to word T1, right? This is again first, second, third, fourth up to T1, right? So the attention matrix is a T1 cross T1 matrix, right? Now what I'm saying is that when I'm looking at the first word, right, I should, or let me start with the second word, right? So when I'm looking at the second word, what should happen? I can attend at the first word, but everything else should be, is that correct? When I'm looking at the third word, okay, not a good choice, and everything else should be 0. So you see what kind of matrix this would look like? A diagonal matrix, a lower triangular matrix. Everyone gets that? Okay. Conceptually, what are the exact dimensions? All that we'll figure out. But you understand the idea. So what are the two concepts that we are thinking of here? One, that you need to feed in the actual outputs. That is known as teacher forcing. What does teacher forcing mean? That you are forcefully feeding it the correct output instead of feeding its own garbage to it. Okay, that's teacher forcing. And the second concept is that while teacher forcing makes sense, you cannot take it to the extreme and feed it the entire sentence. You should mask out things which are not relevant or which are sort of illegal at this point of time. Right? You cannot see the rest of the sentence. Does that make sense, everyone? Yes? So these are the two concepts that we have learned, teacher forcing and masking. Teacher forcing is just an idea, like in the sense that instead of feeding the output from here, I just feed the ground truth. Right? So there's no math involved there. But when I say masking, I need to tell you that how do I do masking? Right? How will I implement the mask function? Right? So that's something that I need to tell you. Okay. So good. So that's what we needed to learn afresh in the case of decoder. Now that we have understood it conceptually, how to implement it or how to convert it into a set of equations, I think that should be straightforward. Okay. So let's start. So this is what the slides say, right? I mean everything that I said in words, that instead of feeding the output from here, okay, let me just do the full animation. Do you understand this concept, everyone? Okay, fine. Okay. So this is what we were doing in self-attention. In the case of encoders, you had this QKV, the query, the key and the value, right? And then you had this matrix multiplication between Q transpose and K. Then you were doing scaling, then computing the softmax, and then doing the multiplication, right? So do you all remember this or not?
Yes.
Right. So this was softmax Q transpose K into V or V transpose, I don't remember. Maybe I'll just write V. And then there was this scaling, right, square root of D. Is that okay? Right. So this is what you are doing. So when you do this, is it a masked attention or a full self-attention? Full self-attention, right? Because every word, this Q transpose K, that is that T cross T matrix that is getting computed, and there all entries are whatever they are. You have not forced any of the entries to be 0. Does that make sense? But now what do you want to do? You want to do masked self-attention. So where will we do the masking is the question. Okay, so we need to figure that out. How will we do the masking? Yeah, so we want the masks to be there. So I've put the mask after the scaling. I don't know what that means, but let's see what that means. Okay, yeah. There's this footnote here that while we are talking about masking in the context of decoders, there's also some masking used in the encoders, right? So when you're training practically, you have assumed a max sequence length of capital T, right? You have assumed that a max sequence length is capital T. Yeah. So what I was saying is that while we are talking about teacher forcing or masking, sorry, not teacher forcing, masking in the context of the decoder, it also happens in the encoder. So in the encoder, what will happen is that you will assume there's a max sequence length, okay? And suppose you have assumed that the max sequence length is 512, then if you have a batch size of 64, that means you'll have 64 inputs and each would be of length 512, right? But what if a particular sentence is actually shorter than 512 tokens, right? So that means you'll just have some pad tokens at the end, right? Is that correct? These would be actual words, I am going blah blah, and then suppose the sentence ends and you have not reached 512 tokens, the remaining tokens would just be pads. Okay. Now when you are computing attention, do you want to pay attention to the pads? No, these are useless tokens. So what should you do? You should dash them away, mask them away, right? So that means you will use masking in the encoder also. So while we are learning it in the context of decoders, just remember that it also happens in the encoder also. Is that fine? Okay, fine. So now the question is, while we agree that masking is important, how do you actually implement it? Okay. So this is what masked self-attention would look like, right? So when you are at the first word, when you are trying to decode the first word, you don't want to pay attention to anything in the decoder, or rather actually you can think of, sorry, my mistake, you could just think of this as a T plus 1 cross T plus 1 matrix, where is the plus 1 coming from? Go, right? So it's coming from go, so this is go. So now at this point, when you're looking at the first word, you only want to pay attention to go. The second word, you only want to pay attention to go and none. The third word, only to go, none and transformer and so on, right? That's how you want this matrix to look like. You don't want to pay attention to anyone else here. Does that make sense? So it looks like this lower triangular matrix as you were saying, okay? If I can somehow ensure that my attention matrix is not QK transpose, okay? Sorry, not Q transpose K, right? Transpose K, yeah. That my attention matrix is not just Q transpose K, but Q transpose K with the constraint that it's lower triangular. Does that make sense? That's what masking says, okay? So how do I do that is the question, right? And that's what we are going to see on this slide. Okay, so this is what our Q1, K1, V1 looks like. We have seen this before. Then let's call Q1 transpose K1 as A, right? And this is what we are passing through the softmax, if you remember. So this, my final attention weights are actually just a softmax of this, if you remember, right? If I just pass it through softmax, of course, scaling by square root of t. Do you remember that, right? So now if I do a softmax on this, this is my T cross T matrix. If this is not lower triangular, right, then the softmax will not make it lower triangular, right. Whatever this is, the softmax would have the same shape, right. So before going to the softmax, looks like I need to do something so that I convert it to lower triangular. Is that okay, everyone? Yes. So now what I propose is, not I propose, what people have proposed. Okay. So these are the alphas that you have. Okay. Now we want them to be 0 whenever we are not allowed to pay attention. Okay. So now what I am going to do is, I am going to do the following. What was A? A was Q transpose K. Okay. I have added a matrix to it. Okay. So remember that A in this case is a T cross T matrix. So if I am adding a matrix M to it, the matrix M should also be a T cross T. Okay, fine. And what should the entries in the matrix M be?
Upper triangular negative.
Okay, so lower triangular you wouldn't want to modify, right? Is that okay? So I'm adding two things and I don't want the lower set of values to change. So what should the lower triangular part of M be? Zeros. Okay. And what should the upper triangular part be?
Negative of upper triangular matrix of
Oh, negative of that. So that it cancels out and A plus M becomes 0. Okay. You said it, I did not say it, okay, but I will go with what you are saying. Okay. So the lower part would then be A as it is after this addition, right? So you are saying A plus M, the lower part would remain A, right? And the upper part would become zeros, is what you are saying. Okay. Is that fine? Now if I do softmax of this, if there is an entry 0, what is the soft value after softmax? E raised to 0 divided by some summation. Okay? E raised to 0 is 1. And let's assume this summation is again a non-zero entity. So there will be 1 divided by some value, right? Let me call it Z. Will this be 0? No. This is what you wanted? No. You wanted it to be 0. Okay. So making this 0 does not seem to be the right thing to do. So what should we make this? When I say this, I am talking about the value before the softmax. So what should this value be so that after you apply softmax to that value, you get a 0? Is that correct? You want the attention weights to be 0. This is the value before the softmax, before the attention weights, right? These are the A's. You want the alphas to be 0. So what should the A's be so that the alpha is? Huh? He says negative infinity. Let's see. So if I make it E minus negative infinity and then divided by Z. So what is E raised to minus infinity? 0 divided by Z. But then what if Z also becomes 0? Will Z be 0? It won't be 0, right? Because one of the elements in this row is non-zero. Is that okay, everyone?
Yeah.
Everyone fine with this? Okay, so you see what the mask matrix should look like, right? And the beauty of this idea is that you have already fixed the sequence length for a batch. It's of size T, right? Now the mask in your idea, which was anyways wrong due to calculation reasons, but the mask was every example specific, right? You were saying that whatever is the A, you make it negative and put it in the mask. But now is the mask example specific? No, it's just a fixed matrix which looks like this. Okay, actually this part, this is a bit of a, this is what A plus M looks like, right? This is not the mask. This is what the mask looks like. Is that okay? And if add this to A, then remember the first entry of A was Q1 dot product K1, the second entry was Q2 dot product K1, Q2 dot product K2 and so on. So those entries will remain as it is because they are getting added to 0, right? But wherever you are not supposed to see those entries will become minus infinity, and now when you do the softmax, e raised to minus infinity would be 0. So those attention weights will become 0. Is this clear, everyone? Okay, so you understand why how masking is done? Okay, good. Okay, just to quickly summarize what we have done, we are zooming into the decoder, okay, and the first sort of new concept that we encountered there was the masked self-attention. So we wanted to understand why we need masking. So that's what we have done in this video. We have understood something known as teacher forcing, why teacher forcing is important, and then a related concept that while you are doing teacher forcing, you cannot take it to the extreme and allow it to see the full sentence. So you need to do masking, right? Then once we understood teacher forcing and masking at a conceptual level, we have then implemented it using a mathematical operation where we say that we introduce a mask matrix and you add it to the attention before softmax, and then when you do the softmax, you get the zeros that you desire, right? So you wanted this lower triangular attention matrix, and the masking has allowed you to do that. Okay, so I'll end this video here, and then we come back and further zoom into the decoder.